Let's get right into the FMGEC behavior and the overall energy state management we saw in the TACA Flight 390 overrun.
Yeah.
Today's deep dive is a closed-door technical debrief covering the sequence of events at Tegucigalpa, Toncontin.
Right. And we are looking at this from a strict systems and human-machine interface perspective today. I mean, we all know the A320 flight control laws,
Yeah.
but seeing how those laws interacted with the crew's mental model during this specific approach is, it's absolutely critical for line operations. We're skipping the basic narrative. We need to dissect the data.
Exactly. So let's establish the initial configuration and the energy state. We are looking at a very heavy aircraft. The structural limit for this airframe, the absolute max landing weight, is 64.5 tons. Flight 390 crossed the fence at 63.5 tons.
So they are effectively right at the maximum certified limit.
Right. And you combine that mass with the environment at TGU, the airport elevation is 3,297 feet.
Which means the air is significantly less dense. To maintain the same lift margin in that thinner air, your true airspeed has to be higher.
Yeah, and then you factor in the weather. We have the remnants of a tropical storm, low clouds, continuous drizzle, and most importantly, a completely wet, ungrooved runway.
That ungrooved aspect is a massive degradation to your braking action.
It really is. Now, let's look at the automation configuration, because this is where the cognitive decoupling starts. They are flying a non-precision approach, breaking out into a visual circle-to-land maneuver.
A very high workload environment.
Extremely high. The autopilot is disconnected, the flight directors are selected off, they are hand-flying. But the autothrust is still engaged, operating in managed speed mode.
Right, and that's a trap. It's a very common trap in mixed automation. The PF, the pilot flying, is actively managing the trajectory with the side stick, but the FMGEC is still commanding the engines to maintain the target VAP.
And their VAP, their target approach speed, was calculated at 137 knots. As they cross the threshold, the indicated airspeed on the PFD is 139 knots.
So from inside the cockpit, looking strictly at the airspeed tape, it looks like a stabilized approach. 2 knots over target is well within limits.
It looks perfectly fine. But here is the critical data point. The FDR confirms they had an estimated 12-knot tailwind.
Which completely changes the physics of the landing.
Exactly. The wings feel 139 knots of airflow, but that tailwind is pushing a 63.5-ton mass over the ground at 159 knots.
Right, and this is a fundamental concept we have to drill into our line pilots. The brakes, the tires, the reverse thrust, they do not care about your indicated airspeed.
Yeah, the pavement only cares about ground speed.
Exactly. Your kinetic energy is a function of mass and ground speed squared. So when you bring 159 knots of ground speed to a restricted, wet runway, your energy state is already critical before the tires even touch the concrete.
Which brings us to the touchdown sequence. Runway 02 at TGU has a displaced threshold of 213 meters. That leaves a landing distance available, the LDA, of just 1,649 meters.
For a heavy A320 on a wet day, 1,649 meters offers zero margin for error. You have to put the aircraft firmly into the touchdown zone.
But they didn't. They carry that excess energy, that 159 knots of ground speed, right into the flare. The report shows they floated an additional 400 meters past the displaced threshold.
Right, they consumed a massive percentage of their usable runway, just bleeding off speed in the air.
And this is where we need to look closely at the aircraft's internal logic. The main landing gear finally makes contact with the runway, but the PF holds the nose wheel off the ground for another 7 seconds.
7 seconds is an eternity in this business.
It really is. So let's trace the logic through the FCOM. What is happening mechanically during those 7 seconds?
Well, the initial main gear compression triggers the weight on wheels, the WW proximity sensors.
Right.
Because the SECs, the spoiler elevator computers, see that main gear compression, they command the ground spoilers to deploy normally.
So spoilers are up, dumping lift.
They are. And the crew selects maximum reverse thrust immediately upon main gear touchdown.
But the nose is still high.
Exactly. The nose is pitched up, meaning the wings are still at an angle of attack where they are generating lift. You are essentially wheelbarrowing down the runway.
So the full 63.5 tons isn't resting firmly on the main struts.
No, it's not. And that fundamentally compromises the BSCU logic.
The braking and steering control unit.
Right. The BSCU reads wheel speed and commanded brake pressure. If the weight of the aircraft isn't firmly pressing those tires into the asphalt, the friction coefficient is terrible.
Because it's a wet, ungrooved runway.
Exactly. So the moment the brakes start to grab, the tires want to skid. The BSCU's anti-skid system detects the impending skid and immediately commands a release of brake pressure.
To prevent a tire blowout.
Right. So for 7 seconds, while the nose is in the air, you are hurtling forward at nearly 80 meters per second, demanding maximum deceleration. But the anti-skid logic is actively preventing the brakes from fully applying because the airframe is still partially flying.
It's a complete degradation of your stopping power. And let's look at the manual braking timeline. The auto brake was armed to medium, but manual pedal braking wasn't applied until 4 seconds after the main gear touchdown.
4 seconds of rolling without manual intervention?
Yeah, and maximum pedal braking wasn't commanded until 10 seconds after main gear touchdown.
Which points to severe task saturation. The PF is fighting the directional control, dealing with the crosswind, the wet runway, and the braking is delayed.
But then we hit the most critical human interface failure in the entire sequence. They are running out of pavement. They are desperately trying to decelerate. The aircraft reaches 70 knots indicated airspeed.
And we all know what happens at 70 knots.
Right. The PM, the pilot monitoring, makes the standard FCTM call out, 70 knots.
It's a condition trigger.
And the PF instinctively pulls the thrust levers from maximum reverse down to idle reverse.
He voluntarily surrenders a massive portion of his stopping power with less than 200 meters of runway remaining.
Exactly 190 meters left. Why does a highly experienced line captain do that?
It's a textbook automation surprise, driven by stress-induced cognitive tunneling.
Let's unpack that for the group.
Sure. In the simulator and on every normal line flight, we train pilots to stow the reversers at 70 knots.
Right, to prevent the engines from re-ingesting their own turbulent exhaust gases, which causes compressor stalls, or to prevent sucking up runway debris.
Exactly. It is a deeply ingrained muscle memory response. You hear 70 knots, your hand automatically pulls the levers to idle.
The habit loop takes over.
It completely overrides analytical thought. In that high-stress environment, the PF lost the situational awareness to realize that standard operating procedures no longer applied.
Yeah, preserving the engines is irrelevant when you are seconds away from going off a 20-meter cliff.
Right. The mental model of the flight completely decoupled from the physical reality of the aircraft. He reacted to an audio cue instead of reacting to the runway and lights rushing toward the windshield.
And the physics? They're unforgiving. They overran the pavement at 54 knots, dropped down the embankment, and that was it.
So we have to look at the systemic verdict here. The investigation didn't just blame the habit loop.
No, the probable cause cited the crew's decision to land without properly assessing the operational conditions.
They completely disregarded operator procedures regarding landing distance assessments.
Right. They never recalculated the max landing weight or the required runway distance for those specific wet conditions before they started the approach.
Which again points to task saturation. They were so fixated on navigating the storm and flying the complex visual circle that they lost the big picture.
The cognitive bandwidth was maxed out just getting to the runway. They didn't have the capacity left to ask if they could actually stop once they got there.
But the report also highlights a significant blind spot from the manufacturer.
Yeah, this is a crucial point regarding Airbus documentation.
The investigation noted that there were no procedures provided in the FCOM or FCTM detailing what a pilot should do if the aircraft touches down well beyond the recommended touchdown zone.
Right. The underlying assumption from the engineers is that if a pilot floats past the 1,000-foot markers, they will simply command 2GA thrust and execute a missed approach.
The system assumes the human will act rationally and flawlessly. It assumes the pilot will suppress target fixation, recognize a deep landing, and go around.
But humans don't operate like that under extreme stress. We get target fixation. You finally see the runway after a grueling approach. You just want to put the plane down.
Which is exactly why we need actionable line pilot takeaways from this debrief. We need mentor insights to prevent this specific type of cognitive tunneling.
So how do we equip our captains to break that habit loop?
First, it's about the briefing. You must brief the ground speed.
Not just the VAP.
Exactly. The FMGC gives you an indicated target, but you need to proactively calculate and verbalize what your ground speed will be over the fence. If you see a 15-knot discrepancy, that needs to be a hard red flag in your energy management mental model.
Right. And what about the touchdown zone discipline?
We need to establish hard limits, and they have to be briefed before top of descent. You brief the PM to make an aggressive call-out.
Like long landing, go around.
Yes. If the main gear isn't firmly on the pavement by the end of the touchdown zone markers, it's a mandatory missed approach. No hesitation, no salvaging the landing.
And regarding the reversers,
The PF needs to consciously brief the non-normal action. If we are heavy and wet, I am keeping max reverse through 70 knots until we are at a safe taxi speed. You have to consciously overwrite the simulator programming before you are in the hot seat.
that proactive briefing is the only way to short-circuit the stress response.
It really is. You have to build the mental model before the workload spikes.
So to wrap this up for you all listening today, the primary takeaway from Flight 390 isn't about stick and rudder skills. It's about preparation and continuous assessment.
Right. The captain was highly skilled to get that aircraft lined up in a storm, but physical skill cannot override a critical energy state.
The time to realize your energy state is unmanageable is at 10,000 feet, not when you have 190 meters of wet asphalt left.
Absolutely.
I want to leave you with a final thought regarding the automation philosophy we rely on every day. Airbus designed the FCOM assuming a perfect operator response to a long flare.
They assumes the go-around.
Right. We fly systems, and frankly, we interact with systems in our daily lives that are engineered with the assumption that the human operator will act flawlessly.
Which is a dangerous baseline.
It is. When a system assumes you won't make a mistake, it rarely builds a robust failsafe for when you inevitably do.
You become the single point of failure.
Exactly. So as you go back to the line, keep questioning the systems you trust. Keep assessing the margins in your environment, because when the margins are razor thin, the physics will always win the argument. Thanks for joining this deep dive.